semantically segmenting the 3D mesh. Well, now I'm in PixMap, actually. It's a small startup from CNRS and INRIA. And we're like a bunch of researchers working on 3D SLAM problem. So as you see here, we're doing like a camera pose estimation based on RGBD camera. And of course, should be in real time. And my task specifically is about geometry reconstruction. So once we have the camera trajectory, which has, we've already found this best pose estimation and done all this loop closure, everything, the next step is to reconstruct the 3D geometry and the texture. Well, what we have done, actually, we divided the whole volume to a smaller sub-volume, as you see here, and considering some small overlap between different sub-volumes. And it's a volumetric reconstruction. As you see, the quality of the texture is not really good. So we have like the next step, which is photometric reconstruction. And as you see at the end, we have to build this geometry, which is encoded in triangular mesh. And also each triangular mesh is associated with a smaller texture map. Well, this texture reconstruction, what we call it. So by just following the camera trajectory, we update the information of every small triangular face. And based on that, as you see here, we are updating this information. We blend different point of view because we gather all the information about all the camera trajectory, finding the best views, blend them together, and then we are reaching this result. I just open it with the Mesh Lab just to show that it's exportable. Well, so this is what I've been doing in PixMap. My research generally, well, I've been always working on 3D vision, as I explained, well, on surface reconstruction, on point cloud registration. Then I moved to deformation modeling. When I joined INRIA in Grenoble, I was working on motion capture system. So we had this huge acquisition room to capture the 3D geometry of the person and the texture information as well. And then the idea was to track or to do matching based on that. And at the same time, I've been always interested on machine learning technique, like the modern techniques, like random forest and recently deep learning. And I've been using that tools for different problems, like multi-class object detection, and also for this presentation. Well, here I will talk about the semantic segmentation. Of course, all of you know that it's a kind of classic problem for 2D images. So the idea is to label the given RGB image to different given labels. There has been many techniques around like graph cut or variational method that is energy-based minimization. And at the same time, the idea is to take care about contextual relation between different labels. So you should know that each part of the object is more likely to appear with the other labels based on some probability distribution. But as you know, deep learning has been a kind of big game changer since a couple of years ago. And there has been solutions for for estimating a kind of MRF model. There already RNN that is doing the job. So there is no need to go through different stages like classification and then smoothing, label smoothing like MRF model. Deep learning is of course doing the job. But in our case, since we are dealing with this 3D mesh, the problem would be a little bit more challenging. So for instance, the kind of data set I was working include like 1 million triangular faces, 3D manifold, plus the photometric information, as you see, is associated there. This data set was provided by another startup in Sofia Antipolis, again, the researcher coming from India. It's called Accu3D. They've been expert on like a structure for motion technique and flying drones around and capturing the geometry and the texture information, as you see here. And why not deep learning? Well, there are many challenges here. For instance, computational part, because we have like 1 million triangular phase, or could be even more. And at the same time, we have also photometric information. And the idea is, well, it's a kind of problem how to merge these different sort of modality there. Well, deep learning could be an option. It's been widely used into the image segmentation. But for our case, since in deep learning, the idea, well, with recent CNN methods, in the first layer, which is the convolutional layer, you're required to provide something in a kind of, in a format of regular grid, because these when you're encoding this kind of neighborhood information, which was formerly encoded in kind of hard descriptor. So these done in the convolutional layer. But in our case, since we are dealing with 3D manifold, it's not really straightforward. And the recent works I've seen by a guy in Princeton, actually. Well, he was previously with Google. And in his case, actually, he's kind of extending this manifold to a kind of volumetric representation. So instead of having this triangular mesh, you would have something volumetric, and then you would have something in regular grid, and you can apply the convolutional network layer on top of that. So because of that, well, we had a different approach just to avoid this kind of expenses. To reduce the computational part, first we just segment the given mesh to a smaller parts. We call them superfacet. It's like an analogy to superpixel into the images. Then we describe these features, different features actually, both geometric and photometric. And then we learn a kind of classifier on top of that. And at the end, we are doing some kind of smoothing, label smoothing. But our intention actually was to use more contextual information. So for instance, for the trees, actually, we always had this problem because the drone was flying on top of the trees. So you never had information on the lower part. So what Accu3D was doing was just reflecting the ground information, just reflecting them on the tree. So you had the lower part of the tree with the wrong color information, which was like brown color, was not green actually. So any kind of classifier would be mistaken here. So the idea is to use kind of contextual information. Well, the first step, we have this superfacet clustering, and we are using some geometric information like shape operator matrix. And also we are respecting the edges just by checking the mean color information. So we are stopping the region growing once the mean color is really changing abruptly. So we are taking photometric information into account, and also the cluster size, everything can be managed by the user. For superfacet description, well, for geometric features, we use something really, really simple. Well, the idea was to be as simple as possible. So we had this elevation. So for that elevation, we consider a kind of local window, a volumetric window. And then we just take care of the Z min, Z max, and then taking these values, which is showing the elevation, just to be discriminative between the ground level and something that is higher, like the roof or the higher part of the facets. And even for this elevation, it's not really straightforward, because in some part of the scene, you would have this hilly situation. So it's really hard to to say which part is the ground, which part is the roof, because some part of the ground can be as high as a roof. The other thing we are carrying is planarity. Then we just extract this covariance matrix, which is just showing the variation over the given superfacet. And then we are extracting that value. So this lambda 0 is the lower, the smaller eigenvalues, and the other are the other two. So if the region is kind of flat, then you're expecting to have lambda 0, 1, 2, all as the same value. So that AP at the end would be 0 if it is planar, and would be 1 or approaching 1 if the region is really bumpy. And that's going to happen for instance, for vegetation or for trees. So again, discriminating between trees and others. And horizontality, because we have the gravity vector, so we can judge how horizontal every superfacet is just by checking the angle with this gravity vector. At the same time, we have this photometric information. As I already explained in previous slide, every triangle is associated with some coordinate in the texture map. So for every triangle, you can go back to the texture map. You can extract all these basic information like average, HSV, and the standard deviation, all this information. And what we have found useful was a histogram of colors. So we had like pre-processing step. We extracted the major color component. And then for the given superfacet, we could easily extract this information. And so these are basically our descriptors. So we're both considering these geometric and photometric. And we are encoding each of them in a single vector. But the other issue that was a problem, I will highlight it in the next slides, is this contextual relation between two superfacets. Just to avoid some kind of weird cases, like if the roof is attached to a kind of, I don't know, ground. It never happens, right? So just to discourage this kind of situation, instead of labeling every superfacet separately, we consider a pair of superfacets. And this information was later on used in MRF, in the Markov random field. So this mistake is inevitable, we know that. But we are going to avoid that mistake when it comes to the label smoothing. So because of that, what we've done, we have come up with a new labeling. So instead of labeling that superfacet itself, we label that superfacet, but in the same time, we consider the neighboring superfacet, and we say that whether this superfacet has the same label as the current superfacet. So this kind of label agreement could be checked then after. So this is how we are extending the set of labels. So if you have like n different classes, well, most of the case is 5 to 6, like the ground, the facet, the roof, vegetation, chimney, etc. These number of labels could be extended to 2n. So we are going to double this number of labels. And well, we always know how this kind of connection between the previous labeling and current labeling is done. And then once we extract this training set, we just simply apply this random forest. Actually, random forest I had already experienced like in 2012 when I was in Imperial College. I was using the regression version of that. And, but fortunately, this is already available nowadays in OpenCV. So simply by random forest, all we need is to provide this training set, which is this concatenated feature vector, the longer one, f hat ij, instead of a single fi or fj. And then to do all these kind of passing through the random forest and to find out the extended label at the end. Yeah, sure.
So why is it not n square labeled if you look at the pairwise label populations?
Yeah, because then the classifier should predict n square labels instead of 2n squares. For instance, if you have like 7 different classes, then you have to predict 49 different labels, but in our case would be 14. So the kind of error in the random forest you will have, which would be much less than.
Well, how do you get it to 14?
Yeah, well, this is how I explained, right? So instead of predicting the label of the neighbor, I say, well, the prediction happens later when it comes to that superfacet. But for the moment, I'm considering this superfacet. All I need is to say this superfacet has the same label or not. Yeah. So I'm not saying, okay, what is this superfacet? And what's the next, by the way? That would be a waste of time, because later on you would go specifically on that superfacet itself, and you judge about the label. But what I'm caring the most is whether this neighboring superfacet has the same label or not, based on this concatenated vector. Well, that's actually useful for the second step when we have this MRF model. Because in MRF model, you will have this data term. So in the data term, you completely focus on every superfacet. So you look at the superfacet. If the prediction, the histogram, tells you that, yeah, it's like 70% vegetation, then you would probably label it as a vegetation. So you can highlight that score much more based on the prediction of the random forest. But at the same time, we have the other label, which is the smoothness term. And in the smoothness term, you have to smooth if two superfacets are likely to be in the same class. For instance, before, you would say that, yeah, check the angle. If the angle is more or less similar, yeah, well, it's less likely to change the label. But in our case, this is how random forest is working for this, predicting this term as well. This is actually the prediction of my random forest. As you see here, is not ask you to approach that. Here in the tree, as you see, this part of the tree is mistakenly labeled as a facet, which is not facet. And you cannot avoid this mistake because in this part, it was not visible for the drone, and it was just the reflection of the ground because we couldn't leave it uncolored, untextured. So you had this wrong texture, and because of that wrong texture, you had this wrong labeling at the end. But at the same time, I don't know if it is obvious or not, we have some black markers here around, here or here. So what is that black marker telling me? This is the encoded information in my random forest. When I was extending my labeling, this is what I was encoded there, I was encoding this information. So if you have the black marker, it tells you, yeah, this is a vegetation, but I'm kind of sure that you're having transition in the labeling. But here, you say that, yeah, this vegetation, this facet, but I'm not sure if there is a transition in the labeling. So this information is highly useful in the MRF part. So that's how we're smoothing this labeling at the end, as you see there. Well, here, just since I like mathematics a lot, I just explain how this conversion between the extended label and the true labeling, the traditional labeling is happening. So how this prediction of the extended label can make my data term for MRF, and how, again, that prediction could help me for this regularization part. Well, this is the software I was developing. Well, this work has just recently been published in a journal publication. When I was at INRIA in Sofia Antipolis with Pierre Allier in the geometry processing team. And as you see, I was just uploading the mesh in the HSV channel. So first I uploaded the mesh, as you see. Well, we're just showing that in HSV channel because it's more discriminating for different parts of the scene. And the next step is to do this superfacet clustering. You can do training as long as you have the ground truth, or you can do directly the testing if you have the final trained random forest. And this is the final result of label smoothing. Maybe I didn't highlight that. Yeah. So I've shown at the same time some kind of noisy black part, and that black markers you see there is how our method is kind of contributing, because we are caring about this contextual relationship and to avoid unlikely situations. I'm just showing that, yeah. So you see these black things there. Whenever I'm sure that I have a label transition, I have these black markers, and then I'm using them in MRF. The other issue in MRF, you have like, you should find a balance between these two different label, data term and smoothness term. Well, in any kind of energy minimization, we had that issue. So if you use lambda, well, sorry, gamma is showing the smoothness term. So if you don't use a smoothness term, then the final prediction will be the prediction provided by random forest. So you're not going to change the result of random forest. But if you increase this value, you're going to smooth, you're going to give more weight to the smoothness term. So get rid of the wrong labeling in this stage. But if you insist too much in that direction, you're going to go to the wrong labeling at the end. Here I'm just highlighting how this photometric information is also important, because if you only use this geometric information, then it's really likely to be mistaken. As you see on top of the tree, they're labeled as a roof. And if you just focus on photometric information, then you simply crash for a simple part like detecting the ground, as you see. Because in this part, no elevation information was used. So because of that, we focus just on the creamy part of the ground, and it was detected as a facet, which is dominant color for facets. Here I'm just showing some analysis to show which kind of information are more useful. Well, color histogram was used the most. As you see, in 50% of the case, I was using this information in my random forest when I was doing these random tests. Well, and also you have for the given clusters and the neighboring cluster, and of course the given cluster is more than 50% of the time used to predict the label and also the neighboring information. Well, this is just to highlight the final labeling. Well, some result. These are provided by Acute 3D. Some scene from Paris, and below you see the sum of the highlighted parts. Well, some parts there are still some mistakes. Well, we couldn't avoid that because in the training examples we had many cases that there was some plant on the facets, and the color here was close to plants. Other results. Well, just a simple comparison. If you use a patch-wise method, you would have some mistakes, as you see, mainly on the vegetation part. But with our method, is much better result because of this extended labeling. Well, here in this example, it's very simple, but the patch voice just crashed there because the local window we consider, there was a small river right there. So this part of the ground was mistakenly labeled as a roof because it has a different elevation than the neighborhood, but it didn't happen for the other case. Well, we just showed that this labeling can be extended if you want to consider like another class, like a chimney, or any other classes like windows again. But the problem was to provide this ground truth because we had to provide them manually, you know. Different type of regions has been considered, like residential, industrial, urban, and hilly regions. For residential region, you see, here is the result. So most of the houses are like on the ground floor or like with 2 floors at max. Well, for industrial region, there are another issues. You have like a huge building with a really long roof, and I will explain later on some result what could be the problem here. And these are the results by our training random method. And some urban region, well, from like different towns of France, yeah, you have like a dense neighborhood of taller building. And the most challenging part was this hilly region. You see, for instance, here you have this creamy color. So it's really likely to say, oh yeah, you have probably fasted. And since the local elevation tells you, yeah, well, here is higher than this part, so it's more likely to be ground here and to be roof there and to be facet in the middle. So that's why you have this strong method. I've just shown this example to highlight that this hilly region could be really a problem. And another problem, even for me, because I was providing this ground truth, sometimes I didn't know if I have to color it as a kind of vegetation, because the color is green. You have some part bumpy, like it's vegetation. So because of this hesitation, you have that result in the random forest. Well, again, I should highlight that in our random forest, if you're dealing with industrial region, you should have already seen this industrial region. Because what's the problem here? You have a huge roof. So when you're in the middle of the roof, and if you consider a local window there, for instance, you look at like 5 meters by 5 meters by 5 meters. Everything looks flat. You have no difference in the elevation. So it's very likely to be ground level. Because in the other scenario, it doesn't happen. Because when you consider 5 or maybe other, like 10 by 10 by 10, it's really likely to have some part in the ground level and some part really high. So you know where is the ground, where is the Z mean. But for industrial region, could not happen. So it's better use kind of trained random forest for these situations. Well, just to highlight all the points, yeah, I presented some semantic segmentation for texture mesh, and the idea was to use contextual information. We were using machine learning, like random forest technique, using both information, geometric and texture. In our case, just to benefit from this contextual information, we trained a random forest for extended labeling so that this labeling can be later on used in MRF model. And yeah, a different region has been examined in these cases. And thank you.
Based on semantic segmentation, can you make an automatic classification between urban areas and industrial areas?
Yeah, well, that could be done by another class because that could be done. Yeah, it's possible. Yeah, because but in our case we didn't consider that. Yeah, you can have another classifier that is telling you which part is which, so which region.
It seems to me so there is a significant variance within urban area
Yeah.
class, right?
Yeah, definitely. Yeah.